Hello, everyone. It is the Prophet Michael David, aka Aries, and I'm making a second video today because I saw one of the comments that I wanted to address on my twin primes solution video. Right, I made it the thumbnail of this video, but I'm also gonna post it right after this, and I will read it right now. So at 1036 on the primes video, 1036, wait, wouldn't 6n squared minus 2n always be even and thus not possible to be prime? Question mark. And then somebody commented this is correct. For what they commented, that is correct. Okay, number one, why would you doubt me? I'm a prophet of God. Just kidding. I am a prophet of God, but I am also a teacher, and I'm supposed to address issues like this until the YouTube channel gets too big and I can't address every question, but this one I can. Plus, it's mathematical and much easier for me. Okay, the main crux of this explanation is we have to go over again between primes, prime squares, and my x numbers. Okay, primes are odd numbers that end with 1, 3, 7, or 9 that cannot be devised or divisible into anything except incremental units. So 7 you can only divide into ones, 13 you can only divide into ones, 17 you can only divide into ones. They have no other divisors. Prime squares are squares of primes, and they have to end in 1 or 9 after 7 squared, basically, after 7. 7 squared is 49, 11 squared is 121, 13 squared is 169. They all end in 1s and 9s after that. My x numbers are modified prime squares. So you take any prime squared, subtract 1, and divide by 6, and you'll get one of my x numbers. So what I was saying about my x numbers in the last video is since all prime squares have to end in 1 or 9, that's the same reason why all my x numbers end in 0 or 8 or 4. In other words, if my x number ends in 0, that means that its prime squared ends in 1. If my x number ends in 8, that means its prime squared has to end in 9. And if my x number ends in 4, you know that it's just a composite odd number because the composite odd number has to end in 5. All right, so now I'm going to describe this geometrically with screenshots and algebraically so you guys can understand it better and or try it out for yourself. Okay, that's the start. That's the times tables with my X numbers colored in. The 5 mod 6 ones are blue and the 7 mod 6 ones are greens. Again, those are modified squares. The actual squares are in purple, but don't worry about those. All right, and then that sheet is just the timetables all modified by that equation that you see at the top of the sheet. So it's basically each cell times 6 plus 1, and then you take the square root of all that, and those are the values in those cells. As you can see, some of the values are whole number values, but a whole lot of them have decimals. That's because that only the numbers that have whole number values are those numbers that are located on the 5 mod 6 line or the 7 mod 6 line. The rest of them will be decimals. So then lastly, what I did is I used what's called a floor function to filter out all of those values that had decimals in them and weren't whole values. That's why they come out as zeros. And then as I described in the last video, I colored all of the numbers to what they were. The blue ones are 5 mod 6 primes. The green ones are 7 mod 6 primes. The orange ones are composites. And the pink ones are prime squares. Okay, now algebraically, you only need two equations to pump these primes out over and over, but you still need to know the rules to do it most efficiently. But here are the two equations. And remember from my last video that the last digits of my x numbers repeat over and over and over as follows. All right, now we'll do a quick walkthrough and I'll do a couple of calculations with you guys. Remember, 36n squared minus 12n plus 1, the square root of all that is the 5 mod 6 primes. 36n squared plus 12n plus 1, square root of all that is the 7 mod 6 primes. So when you hear me say we're checking up, that means we're checking the 5 mod 6 line for primes. And when I say we're checking down, we're checking the 7 mod 6 line for primes. They're not always going to be primes, but sometimes they'll be composites. But primes are pretty dense, especially when you contain them to two separate lines only. Okay, here we go. The first two sets we have to check up and down because, like I said, the pattern doesn't start until n equals 3. So here we go, n equals 1. All right, n equals 1 check up is the check on the 5 mod 6 line. We know it's going to end in 4, but we got to check this one anyway. So 1 squared times 36 is 36, minus 12n is 24, plus 1 is 25, square root of that is 5. Prime check, it's a prime. But again, 5 is weird because it's the only prime that ends in 5. Any other x number that ends with 4, you don't have to check. That's the only one we have to check that is an x number that ends with 4. All right, n equals 1, check down, which is a check on the 7 mod 6 line. All right, 1 squared times 36 is 36, plus 12 times 1 is 48, plus 1 is 49, square root is 7. Prime check, yep, 7's prime. N equals 2, check up. So 2 squared is 4, times 36 is 144, minus 12 times 2, which is 24, which equals 120, plus 1 is 121, square root of that is 11, prime check, yes, 11 is prime. N equals 2, check down. Again, 2 squared is 4, times 36 is 144, plus 12 times 2 is 24, which equals 168, plus 1 is 169, square root of that is 13, prime check. Is 13 prime? Yes, it is. But then after that, the pattern starts and it repeats. And as I've described before, on the 5 mod 6 line, starting with n equals 3, the pattern is 88040. And for the 7 mod 6 line at n equals 3, the pattern starts and repeats as 04088. They're mirror images of each other. So then, in conclusion, starting with n equals 3, all you have to do to check the 5 mod 6 line, is take the square root of the quantity 36 n squared minus 12n plus 1, and to check down, to check the 7 mod 6 line, all you have to do is take the square root of the quantity 36 n squared plus 12n plus 1. But you only have to check them when the x numbers end with 0 or 8. All right, so I'm going to post the pattern one more time, and then I'm going to go through it real quick, and then you guys should be able to understand it. And then, like I said, you can make a computer program and probably pump out as many primes as you want. I mean, you have to prime check them, but you can use the Pascal's triangle technique to do it pretty efficiently these days, even with large primes, and with small primes, it's really easy. All right, here we go. Here we go. Almost to the end of the day. So we're skipping the first two. We're starting at the box because that's where the pattern starts. But so logically speaking, n equals 3, check up. Do we have to check it? Yes, it ends with 8. We have to check it. N equals 3, check down. Do we have to check it? Ends with 0. Yeah, we have to check it. N equals 4, check up. 8. Yep. N equals 4, check down. No, it ends with 4, which means that it's an odd number that ends with 5 and it can't be prime. All right, n equals 5, check up 0, yep. Check down 0, yep. N equals 6, check up 4, nope, don't have to check it. Check down 8, yep, we got to check that one. And then n equals 8. Check up 0, yep, we got to check it. Check down 8, yep, we got to check it. That's the repeating pattern. You don't have to check them all, but you got to check the ones that end with zeros and eights. All right, finally signing off for the day. As always, y'all have a good day or night wherever you're from. Rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are ticked down, aka try not to lie. All right, I'll talk to y'all later.